Well, welcome to our new unit, forces. You may recall, if you saw this as a freshman, if you were here in Newton North, then you talked about Newton's first law, also known as the law of inertia, which expresses that an object in motion remains in motion, an object at rest remains at rest unless acted on by an outside force. The basic idea there is that balanced forces result in no change of motion, no acceleration, which means no increase of velocity, no decrease of velocity, and no change in direction. No speeding up, no slowing down, no turning. However, unbalanced forces, well, any of those can change. You're either going to speed up, slow down, or turn in some direction. Yes, there will be some acceleration. Newton's second law addresses to what degree that happens. The acceleration itself is due to the net force divided by the total mass. So if you've got something like, a box, for example, with 10 newtons pulling it in one direction and 3 newtons pulling it in the other direction, and let's say it has a mass of 7 kilograms, well, the net force is going to be found by taking the difference of the forces in opposite directions. We've got 10 to the right minus 3 to the left divided by the mass, which is 7 kilograms. So we've got a net force of 7 newtons and a mass of 7 kilograms, and that's going to result in an acceleration of 1 meter per second squared. So the greater the net force is, the greater the unbalanced force is, the quicker it will accelerate, speed up, slow down, change direction. And the greater the mass is, the more inertia there is, the more that change will be resisted. And Newton's third law is the equal and opposite forces law. For every force, there is an equal and opposite force, which is to say that when two things interact with each other, let's ignore everything else in the universe and only boil this down to two objects. Let's say the sun and the earth. Sun, earth. Well, the sun certainly exerts a gravitational force on the earth, but in turn, the earth exerts a gravitational force back on the sun with the same amount of force. It's the same strength of push or pull, rather, in both directions. Why does the Earth go around the sun? Well, the Earth's mass is much, much smaller. So the Earth's motion will be affected more than the sun's motion will be, even though they've got the exact same force exerted on each other. Another potential for a situation like that is as simple as a box on the floor. And if the box is sitting on the floor and exerting a force downward on the floor, I'm going to call that a normal force, then a normal force will also be exerted on the box upward by the floor onto the box. And those two forces are going to be equal and opposite. So that's describing the interaction between two objects, recognizing that the force of that interaction is the same on each object. So let's consider the many forces that exist. I'm not going to read every one of these definitions, but it's here for you when you're ready. The key ideas are that a normal force is a contact force. The contact between any two objects, oftentimes it's thought of as an applied force, but when you apply a force to a thing, you're pushing it, you're touching it. And so a normal force is a contact force. Tension force exists when there is a rope or chain or some string, some narrow thing holding two things together. Tension only pulls. You can't push a wet noodle. You can only pull on it. Weight, the gravitational force, exists. I wish the word gravity was used in here somewhere, but that's what we're talking about when we say gravity. an object weighs something because, one, it has mass, and two, because there is some large body in the vicinity that applies a gravitational field, around which exists a gravitational field. And so by virtue of having mass, the object with mass will be pulled towards they'll be pulled towards one another. But usually, when you're talking about a planet, the planet doesn't do a lot of moving. So the gravitational force itself has a formula. That gravitational force is mass times gravity. An elastic or spring force is similar to a tension force, but with a spring or something stretchy, something that can compress or stretch. Air resistance is a result of something moving through the air, also known as drag, and that force is going to be in the opposite direction of the object's motion. If the object is moving forward through the air resistance will be in the opposite direction. Static friction is the force of two surfaces that are gripping each other, just like your feet on the floor when you walk forward, or the force that allows me to hold this pencil in the air. The grippy force of friction between my fingers and the pencil are what prevents the pencil from falling to the ground. So that's static friction. They are sticking together. Whereas kinetic friction is the force that exists when two things are moving past each other. Two surfaces are in contact, but are allowed to move past each other. That's kinetic, the force of friction when things are moving relative to each other. So let's get into it. We've got some things to keep in mind when we are looking at static applications of these forces. One, primarily, is this thing called a free body diagram. We need to diagram the forces acting on this object. Consider Chill Monkey. Chill Monkey don't care. If you're familiar with Honey Badger, it's the same degree of not caring, but with a different character. Chill Monkey has a mass of 15 kilograms. How much tension is in Chill Monkey's arm? All right, so I'm going to represent Chill Monkey with a very modest diagram of a dot. A free body diagram is simply a simplified version of representation of the forces acting on an object. So Chill Monkey has a mass of 15 kilograms. All right, well, I'm going to just draw, I'm going to label this. All right, so there's a gravitational force, which I know something about because the gravitational force equals mass times gravity, and gravity is 10 meters per second squared. So this gravitational force is mass 15 kilograms times 10 meters per second squared is 150 newtons. And we wonder how much tension is in Chill Monkey's arm. Force, tension. All right, step one, I've drawn a free body diagram. Step two, I need to turn that free body diagram into a Newton's second law statement, which says the net force equals mass times acceleration. Well, let's break that apart a little bit. The net force itself consists of a tension force upward, so I'm going to indicate that as positive, and the gravitational force downward, so I'm going to subtract that. And those two together equal mass times acceleration. Well, as you could probably tell from this monkey, the acceleration is 0, so those net forces add up to 0. The tension force minus gravitational force equals 0. A quick rearrangement, force of tension equals force gravity, and so we find that the force of tension equals 150 newtons. An important note about this is I'm using this subtraction sign to imply direction. Another way of indicating or solving this would be to say force of tension plus the force of gravity due to gravity equals 0, where I plug in negative 150 for the force of gravity, indicating that that force is downward. Somewhere I've got to account for this negative. So those are two different ways you could do it. You could literally take the sum of the two forces, where one of them is negative, Or you can choose to use absolute values of forces and let the negative in your equation indicate the direction. All right, moving on. Y monkey, why not? Y monkey has a mass of 10 kilograms. The arm on the left is elevated at 60 degrees. Elevated, all right, so that is, I need a better color for that. That is this angle right here. The angle, the arm on the right is elevated at 70 degrees. And we would like to know how much tension is in each arm. And we'll ignore the mass of the arms themselves. So again, I've got to draw a free body diagram. Here is monkey. Monkey has mass of 10 kilograms, so that is my gravitational force, which turns out to be 100 newtons. We've got a force vector tension. I'm going to call this tension 1 in that direction, and I'm going to call this force of tension 2 in that direction. And I've got a couple angles, 70 degrees here and 60 degrees here. Well, in this case, we've got forces occurring in multiple dimensions. So I need to break this down, just like when we did with projectiles. We break things down into X and Y. We're going to do the very same thing here. I'm going to consider the forces in the X direction, and I can tell that this monkey is at rest. So I'm going to say that the sum of the forces in the X direction are 0, which is another way of saying the net force is equal to mass times acceleration, which in this case is 0. But a recognition that the net force is 0 in the X direction, well, I guess I need to figure out what are my forces in the X direction. Well, I've got force of tension 1 in the X direction. I'm realizing my subscripts are getting pretty busy, so I'm going to back up here a little bit. And depending on your textbook, depending on your teacher, you might see things written differently. You could also just call this big T, tension. Tension 1, tension 2. So I'm going to say tension 1 in the X direction, it's pointing to the right, minus tension 2 in the X direction equals 0. The only two forces acting sideways are whatever X component of one arm and the X component of the other arm. But that doesn't get me very far because I don't know what either of those tensions are. So I guess I need to look in the Y direction. And I can say that the sum of the forces in the Y direction is also 0 because this monkey is not accelerating up or down. That direction, I do know something. I know the weight of this monkey. I still don't know anything about the tensions, but I can say tension 1 in the Y direction plus tension 2 in the Y direction, because both Y components of the arms are pointing up, minus Fg equals 0. So I've got 3 forces in the Y direction. So that's my general equation. Now I can start to get specific. T1x, T1y, I can come up with expressions for those. T1x is going to be whatever the tension is times the cosine of 70 degrees. Cosine of 70 degrees is 0.34. So 0.34 T1. The tension in the Y direction, T1 sine of 70 degrees, is going to be 0.94 times tension 1. I'm going to move this over to the side a little bit, get that out of the way. T2x is going to be whatever T2 is times the cosine of 60 degrees, which is 0.5. So that's going to be 0.5 times the tension, tension 2. And T2y is going to be T2 times the sine of 60 degrees. Which is 0.87 T2. All right, so now I actually have a little bit more detailed expressions that I can plug in. So T1x. Now let's say with the y direction first. T1y is 0.94 times T1 plus T2y, which is 0.87 T2, minus Fg equals 0. Well, I can add Fg to the other side, and I actually have a value for that. So those two combined equal 100. In the x direction, we've got T1x, so that's 0.34 T1, pulling to the right, minus T2x, which is 0.5 T2, pulling to the left, equals 0. So 0.34 T1 equals 0.5 T2. All right, well, I've got two unknowns and I've got two equations, so it's a system of equations. So if I multiply this all by 2, I find that T2 equals 0.68 T1, and then I can substitute that in there. So I've got 0.94 T1 plus 0.87 times 0.68 T1 equals 100. So 0.68 times 0.87 gives me 0.59 T1 plus 0.94 T1 equals 100. So that's 1.53 T1 equals 100. T1 equals 65.3 newtons. And now that I've found that answer, I can sub it back into the other side to find that T2 equals 0.68 times T1, which is 65.3. T2 equals 44.4 newtons. We're going to look at one more example of a chill monkey in a tree. In this case, this monkey has one arm extended in this direction. I'm going to call that tension. Monkey still has its weight straight downward. But when looking at this branch or this tree, in order for the monkey to not be falling or swinging to the right, that tells us that the force exerted by the tree has to be somewhat up and to the left. And that would be a normal force. In contact, normal forces are exerted perpendicular to a surface. So we've got a normal force up and to the left, and we're given some angles. This arm is angled up at 70 degrees, and this feet are angled down at 10 degrees. So we can say that relative to the parallel, that angle right there is 10 degrees. So in setting up this problem, we still need to address all of the forces in the x direction and all of the forces in the y direction. In the x direction, you can say that the sum of the forces in the x direction equals 0 because this monkey is at rest. The forces are balanced. In the x direction, we've got T1 in the x direction to be determined. We've got, and that's to the right, so I'll call that positive. And to the left, I've got the normal force in the x direction. And those are the only x direction forces. Gravity, the weight of the monkey, is straight down. So those two forces alone combine to give 0 net force. The T1 in the x direction, T1, well, the x component would be cosine of 70 degrees minus the normal force in the x direction would be times the cosine of 10 degrees equals 0. So if I plug some numbers in, cosine of 70 is 0.34. So I get 0.34 T1 minus 0.98 of the normal force equals 0. I guess I don't need to label this T1. There's only one tension. So tension. In the y direction, the sum of the forces in the y direction are also 0. In the y direction, I've got 3 forces. I've got T1y plus the normal force in the y direction minus gravitational force, and those all combine to be 0. So the tension in the y direction is going to be whatever the tension is, sine times the sine of 70 degrees plus the normal force times the sine of 10 degrees. And those are balanced by the weight of this monkey, which is 15 kilograms. So that's 150 newtons. So I've got tension times sine of 70. So that's 0.94 times the tension plus the y component of the normal force. So that's going to be sine of 10 is 0.17 times the normal force equals 150 newtons. And again, we've got, I'm going to do this in squiggles because these aren't the final answer, but we need these to get forward from here. We've got 2 equations and 2 unknowns. So again, we need to perform a system of equations. I'll let you do that. Lastly, systems with contact forces, multiple objects all interacting with each other. A box 1 of mass M1 sits atop a 25 kilogram box, number 2, and a third box of mass M3. A scale between box 1 and 2 registers a force of 85 newtons. A scale between box 1 and 3 registers 65 newtons. A scale beneath all the boxes registers a force of 500 newtons. What is the mass of box 1? What's the mass of box 3? Well, it seems like I maybe know a lot about box 1 and box 2. Let's start with box 1. I am going to draw a free body diagram of box 1. There are 2 scales beneath box 1, so that implies that there are 2 independent upward forces acting on it. And I'm told that those are 85 newtons and 65 newtons. So I've got 85 newtons and 65 newtons. And the box itself is going to have its own weight. So box number 1 can be addressed just by the forces acting on it. So in the y direction, there are only forces. So the sum of the forces in the y direction are 0. And I've got 85 up and 65 up minus the gravitational force. So the weight of the box equals 0. So that's 150 equals the gravitational force. And that's 150 newtons. And I'm asked, what is the mass? Well, Fg is mass times gravity. So gravity, again, is 10 meters per second squared. So 150 newtons equals mass times 10. The mass is 15 kilograms. All right, so far so good. Now I'm told that the scale beneath everything reads a force of 500 newtons. So I'm going to consider this entire system. I've got an entire system which I'm going to lump together as mass 1, mass 2, and mass 3. And all together, a force of 500 newtons is registered by the scale. The scale is beneath this whole system, so that scale is applying an upward force of 500 newtons, which tells me that if it's imbalanced, then the force of the first box plus the force of the second box plus the force gravity of the third box, all being downward. I guess I'll call those minus. They're all downward. The weight of all 3 of those plus that 500 newtons upward equals 0. We got a 500 Newton upward force that's being used to balance the weight of all 3 of these. So the weight of all 3 of those is downward. Well, now I can plug in some things that I know. I know that the weight of the first box is 150 newtons. I know that the Oh, I guess I don't know the weight of... I do. The weight of box 2 is 250 newtons, and so that leaves me looking for the weight of box 3. I guess I'll move this over to the other side, so that's minus 500, and now I can make everything positive, so that leaves me to solve for the weight of box 3. 500 minus 400 leaves me 100 newtons. And I almost forgot the last step. We actually want to find the mass. So the mass of this thing times gravity, 10 equals 100. So the mass is going to be 10 kilograms. Mass of 3 equals 10 kilograms. The end.